Previous chapter, you are looking at external forces. Now, this chapter, you look at internal forces. Okay. So again, cables is optional for this module, right? Now, you see all these structures in construction and also for aerospace, you see this one in the body wing structure, right? Yeah. So why we need to know that this internal loading is important? Because you know that shear force might make the structure fail. It's like a scissor. If there is no unbalanced force, they push each other, any steel will break. Right? Okay, so how do we do internal loading? We are use a method called section. Means we cut the object into a few components. And we see it one by one. Right? Finding the internal loading at point B, for example, this one. Right? We start with a small, very simple structure. You see this one, you should be able to do what is the support loading here. All right, it's inside the wall. So there's two forces at point A with the moment. All right, and you have an external force P1 and P2. So this is a 2D problem. So 2D problem, we always break into x-axis and y-axis. And then you balance it, all forces in x equals 0, all moment in x equals 0, and so on. Then you'll find, after that, you find resultant and find the angle. Okay. Now, we look into internal forces at B. What happened at B? All right. All right. So we are going to break into B. So when you break B, you cut B. Of course, I should do it very slowly, but I try to explain. So before you cut, you should find external forces first. For internal loading, before you find any internal loading, you need to solve what are the forces at any point that involve external forces. For example, these cases, you need to solve point A forces first. Or at least you label there's a force at A. Like for example, AX, AY, and there's a moment A that is anti-clockwise. That is my method. So I always assume forces go up positive, go to the right positive, anti-clockwise positive. Yeah, solve for A first. Not solve lah, but at least you break it. There's a forces at A, right? Now, if the question asks you to find internal forces at B, so what you do, you break the component into two parts and then you redraw the component, like what you see on the screen here. Right? So you break point B, two parts on the left and on the right. Okay, we start with the left-hand side first. You ignore the B first. Ignore the B, you do the left-hand side first. Left-hand side, you only need to important internal forces. You need to balance. If you not balance, the thing will move by magic. So if the thing do not move, mean the forces must be balanced. For example, B. If you break down, B, you cut it off, it must balance on the left and right. For example, here, when you cut, so here, NB, you draw, there's a rules, when there's an opening, when you cut an opening, when you cut the opening, there's a normal force that join them together. And the thumb of rules, no matter you assume first, when there's an opening, normal force always point out first. You assume point out first. Then only you do calculation. Okay, so for B, there's opening. So opening NB, N means normal forces that is perpendicular to the area. Normal B up. And then there's a shear force that cut down. So here, although you can draw up, but you know that on the left-hand side, there's a shear force AY go up. So what you do, on the left, you always this one, you draw down lah. Okay. So on the V V in static will represent as shear force. In internal forces chapter, we use V is not velocity, but V is a shear force, means the cutting forces. So VB go down on the V, and there's a moment. Moment in this case, we assume anti-clockwise also. So you solve for the left-hand side first. So cutting faces always pointing out. And then shear forces. Shear forces, there's a rules later, I will further detail. Shear forces, you can draw up also, but usually I will just, if there is a sign on the left, I just balance it. I just inverted the vertical forces to another side. So in this case, it's point down, right? You might ask, hey, Dr. Ang, can I point out? Not can. But later when you find, your calculation also, you'll find it's point down. Okay. So any question for the component on the left? No, Any question? No, then we move to the right. Right hand side, basically, you flip everything that you draw on the B point on the left there here. So on the B point on the right, always opening point out. Also, opening point out. VB is must flip with another side. So this side, if left hand side go down, right hand side must go up, so that it balance. There's zero shear force, because actually the real one do not break. You just imagining you cut it. So this VB must be balanced. So one go down, one go up, so cancel. But for static, you need to imagine there is a shear force, because the question asks you to find internal forces there. Okay, now this one VB, it become clockwise because you must cancel the moment in another side. So basically, this area, it must, actually there's nothing there. You just create some forces to do your analysis. Yeah, so the principle is quite simple. We do not touch the external force here. We just do how we do the cutting. Okay, so far okay. All right, so next, the rest already I did explain what is NB. All right, so shear force. Okay, this M, capital MB, is a coupled moment, or we call it bending moment. So this is a bit different from what you learned previously. If you find external forces, it's a moment. Well, you can call it bending moment also, but this one internal is it will cause the structure to bend. So in the steel, because you can precast it, you can preload it. So when you have preload, then the steel, when you release it, it will bend. Or it can go into a certain shape if you want. So if the question asks you to find bending moment for chapter 5, then you know lah. Actually, it asks you to find internal forces of M inside there, along the cutting plane. Okay. So we actually, how we balance the force, actually use back the Newton's third law, where we balance all the force equals 0. Right. Newton's third law means there's a reaction. There's a reaction force to balance it. Right. Okay. There's another method we call equation of equilibrium, which is this one. All the force equals 0, all moment equals 0. Right. But again, what is important, you're able to draw this kind of diagram. Okay. Yeah, so any section you sure will have bending moment, you sure have normal forces, you sure have shear forces. These three things must have for internal force analysis. These three things must have any section that you cut must have moment, must have normal force, must have shear force. These three must have one. Okay. So these are the three-dimensional. So I think, I'm not sure your final got or not lah. But if you have 3D, the concept still same. So you have three axes. So, okay, so again, use your right hands, right? So the normal force, this is y direction. The direction of M moment or torsion is following your finger, your finger curve lah. Right? This is My, this is Mz, this is Mx. If you solve 3D, you use your right hand rules. You ask you the direction of moment, where is the direction? Right? Does it go up or go down? This is on the screw mechanism. So on aircraft, if you have vibration, your screw can auto unscrew and screw. So that's why we don't use screw in the bolt and nut in aircraft because of vibration. Okay, so this one is additional info for you guys. Okay, okay, we go into analysis already. Okay, signal conversion. Again, three important forces: normal, shear, and moment. If you have cutting, first side always pointing up, but facing each other. First scenario, this one is by muscle memory, means you see, if you cut already, there's always normal force look like this, the first one. This is like a law already. You don't need to think one. Yes. So we may actually use static as a basic. Okay. So, and if you have a normal forces at both ends, then it will go out lah. We assume always have a tension force. Right? Means that if you have a surface, always force will go up from the surface. We assume always come up from the surface. That's a hypothesis to make our life easier, because we always like you use positive value. Okay, second set. On the left is normal force. Middle one is a positive shear. Positive normal force means what? Means we assume positive direction of our forces. Same with positive shear force. If you have opening, we always have anti-clockwise rotation. If you see it as a rotation, right? So on the left, always point down. On the right, always point up. By conventional, means if you want to solve any internal problem, you cut it. The visual one like this, the left hand component will point down, right hand component will point up. No need to think one. It's a way of doing things. Okay. Then if it's outside, if you cut outside the thing outside, the left hand side always point up, right hand side always point down. The top one is internal, outside is external. Means if I chop, if I cut this one, what is happened in the middle, you refer to the center. And if this one, if you move like this, if you cut here, the both end will look like this. If you want to find shear force at the end of the object, then you do this one. If you want to see internal, then you use the top one. Yeah, you can see the difference. The top diagram is internal forces. I mean the internal section. The bottom one is actually outside. Normal forces, external surfaces. Yeah, it depends the question. Whether the question asks you what and what. If you cut one, section one, you use the top. If the question asks you to find near the wall, the shear force near the wall, then you use this one. Moment, positive moment, also same. Moment for the left, you do clockwise, sorry, anti-clockwise. On the right, you use clockwise. This one is on the again on the top is what you cut what you cut, and then below one is positive moment, meaning you imagine you bend it that the structure will smile. You bend like this, right? You bend this object, it will smile, right? So smile always positive. Yeah. Okay, so these are the standard practice every time you solve internal problem question. Once you have this one, means you set your all the answer in positive, normal force, positive shear force, positive moment. These three important parameter. Okay. Okay, procedure, this one, we'll come back to this one when we solve one by one. Again, before you solve internal, always solve for support, that the one that I give you, the diagram, always solve for the support reaction first. See what attached to it. Is it a roller built inside a wall, or there's a chain there, right? So determine the support reaction first. Then only you draw free body diagram. This one you can read it later on. Basically, there are two big steps: soft reaction, external one. Then go and cut the object. Use the positive shear force, moment, and shear, normal force, and moment. Okay. Then use equation of equilibrium. So after you draw free body diagram, straight away write this one. All the force equals 0, all the moment equals 0. Then solve lah. Look at x direction, all the force equals 0. Then y direction 0, and so on. Yeah. So again, if you arrive at negative number, this is when you solve and calculate. When you arrive at answer that's given negative, it means what you draw in the diagram is wrong. You need to flip your diagram. Means you get negative in your answer, you write, let's say the one I write here. If you get moment at A equal negative 10 meter per second, the next conclusion, you need to write for marking. Moment at A equal to 10 Newton meter, what is the correct direction? Or if you're lazy to write, you just, for example, this one in your diagram is anti-clockwise. So here you draw clockwise positive. Okay. So some lecturer will require you to redraw the whole free body diagram. So you need to ask Dr. Nuru whether you need to redraw or not, or just make a notation in your calculation. Okay. All right. So just an exercise. So determine normal force, shear force, and bending moment. So again, N, V, and M acting just on the left, point B, and just on the right, point C, of the 6 kilonewton force on the beam. Okay, what are the external force at A and D? The force is pointing. First step, solve external force first. Means you draw the body. You still draw the body. Copy the external force given. Solve for A. Not solve lah, but find the reaction at A and D first. Right? So refer to the diagram that I give you. So A is like a roller, like a ball, right? ball, you imagine there's always one contact point. So always, there's only one contact point here. It is always 90 degrees. So external force, you draw here A equal to AY. Then look at D. D is not a roller, but there's a pin there. The pin means what? You're able to move, right? So there's no moment there. But it's unable to move up and down, left, right. So there is a dx and dy. Okay. So solve that one. I'll show you the next step. So free body diagram, you draw all the dimension, put in external forces. Copy all the forces there. Okay. From here to here should be no issue so far. Some of you might lazy to write the dimension, but I highly recommend you draw the dimension. If not, later when you calculate moment, some of you, your brain might play games with you. Okay. Okay, so as you can see, we are using all the positive forces or positive direction for our assumption. Again, this all our assume the green color is, we assume is going up. We assume. So means the green color one, it might be flipped if you get negative. It might be flip direction if you get negative. If you analyze, you calculate, you get negative, means what you draw is wrong. Okay. So from here, we are solving external first. Can you solve all the unknown here? Can, right? So force the, so AY dy equal to 6. Dx equal 0. Okay. So of course, how you write here, this one, write this one. Okay, right? You can solve moment first or force first, also same. So here I solve at point, okay, moment, there's a trick there. When we solve all the moment equals 0, again, anti-clockwise is positive. And I personally recommend, if you see the diagram that have a lot of forces, a lot of moment one, go to that point and put it there. You find a moment at that point, then you cancel all the forces and moment already. That is the trick. Why we find moment at D? Because once you put your finger at D, you cannot see the moment at this point. Unless the external one. Yeah. So if you, because here you got two unknown, dy dx. You put it here, you only have one unknown. If you see that place a lot of forces one, go and find a moment there, put there, that point. Then you only solve for, you become more simpler like your equation. Okay, so here, I think you should able to see y positive, 1 negative. So 9 kilonewton per 9 kilonewton per meter. This one I just follow. Y positive? Because it's anti-clockwise. We already say anti-clockwise positive. Always fix to that direction. Don't suddenly halfway you change direction. No, always fix to one direction from the start until begin and the end. All right. So here, y negative ay multiply 9. Y negative, because if you put your hand here and you are swing, A is going this way, right? So it's clockwise. But your sign positive is anti-clockwise. So this is clockwise, your positive is anti-clockwise, so it becomes negative. Then here also 6. 6, you put here, 6 go down anti-clockwise, so it's positive. 6, 6, right? So this step is important. You need to write. Don't suddenly land at a number that we are unable to trace whether you understand or not. Okay, so here, the next step, maybe you no need to expand on it. Straight away find what is your AY. AY to 5 kilonewton. And if you get positive value, means what you guess is correct. Make sense, huh? Okay. Okay, once you find AY, you should be able to find DY. Okay. Okay, huh? So when you find AY, so moment you already used already. So you already solve for moment already. Solve for forces, huh? Because you only left out DY, DX, you also, you know it's 0, but still mathematically you need to prove it's 0. Okay, so just the same. The rest, okay, the rest is dy is 1. If I say dy is 1, you should ever understand, right? Or the force in y equals 0. Right? So go up positive. So ay, maybe I write here. All the force, okay, direction, go up positive. All the forces in y equals 0. So I refer to the diagram, ay go up, so ay positive, plus negative, the next one is 6 kilonewton. Then dy go up, so positive dy equals 0. Then I have ay already, I substitute from the previous one, 5 kilonewton minus 6 kilonewton plus dy equals 0, dy equal to 1 kilonewton. So positive means direction correct. Okay, do the same for x. Again, give us direction. What is your positive direction? So always draw positive to the left, positive, sorry, to the right, positive, equal 0. So what are the x? So you only have dx equal 0. So you find all value already. Okay, this is how you solve. Okay. Now we start to see on the left-hand side, because the question asks you to find what is the forces at point B. It is just a little bit to the left of the 6 kilonewton. Okay. So what you do, you need to draw a box, or no need to draw box also. But in your, when you solve, you need to know, tell yourself you're actually solving for AB. So AB, you solving this one. So what you do, you draw AB box, right? A label A and B. Copy the external forces from the diagram. You look on the left and right. Then you copy, you just type from a little bit to the left of 6 kilonewton, means there's no 6 kilonewton there yet. At B, there's no 6 kilonewton yet. So you only see 5 kilonewton at A. Right? Then copy the dimension. It's good not to directly substitute the value that you find. Don't overconfident. Always substitute, always write the unknown, like for example, in this case, A, Y there, just to be safe. Who knows the value you write here is wrong? Who knows? Then the whole question wrong already. Okay, so when you draw free body diagram, don't substitute value that you calculate. Substitute unknown with the unknown labeling, like for example, A1. just to be safe. Just to be safe. Okay. So this one, so here I just put a statement here. The moment of 9 kilonewton meter, we do not include in this diagram because it's involved with the right segment. So again, we are cutting, right? So normal force always pointing out from the surface. So there's a NB. So there are three forces. Normal force, shear force, moment always come together when you cut the opening, right? Why this side is going down? Because we always use a positive shear diagram or positive shear, apa tu? Positive shear numbers. So VB go down because it's on the left. Then moment like this one. Moment and V go away. You're still following the positive diagram that I showed you just now. We just assume the direction like this. Okay. Why? Because all the numbers that we determine all positive value, which means what we assume so far is correct. Okay. Let's say what you see, what you find here is negative. When you find negative, when you substitute value, when remember to substitute the negative value. Although your diagram show like this, let's say you find negative value, carry the negative value in your calculation. Okay. Any question for this small section? No, okay. So solve using this one, equilibrium. There are three steps only. First, solve external forces, support, convert free body diagram. Next, you cut the component, you see three forces: shear forces, normal forces, bending moment. Then your job done already. Go and solve all the force equals 0, all the moment 0 by using that diagram. This diagram. Okay. Solve in the equation format. Don't so eager to substitute value yet. Find the equation first. Right? So for section AB, all the force equals 0. So you can start with moment, you can start with force. So in this case, we start with forces. X direction, go to the right is positive. So here, you only have one NB. Right? So you start with these three equations. My marking scheme always, when you write this one, got 3 marks already. But I don't know Dr. Nurul's marking scheme. My one, you write these 3, you got 3 marks already. But I don't know. Every lecturer have own style. Okay, the rest I think you should be able to understand how to do. The next job is just substitution and then find the unknown. Okay, so first one, all the force in x direction equals 0. If you refer to the diagram, you know NB equals 0. Means the product of the first equation, you find NB equals 0. Don't jump. When you solve problems, don't write somewhere too far from this equation. If not, then we have question mark how you find NB. Okay. Second one, Y. So AY go up positive, NB negative, and there's no Y anymore. So AY negative, VB equals 0. So AY equal to VB. And you know that AY from the previous one, AY is 5 kilonewton. So VB equal to 5 kilonewton. Same with moment. Again, moment, we like to put in the area that has lots of forces that we do not know. That's why you put a moment at B and not A. You put at A, you're asking trouble. because you don't know you're not sure your VV correct or not. If you put an A, you need to find BV, and B don't have because there's no perpendicular distance that turn the pin. Right? Okay. So you put at B, you have AY. AY clockwise is negative because here anti-clockwise positive. So normally careless mistake is here. You already write anti-clockwise positive, but when you do this one, you always forget this is clockwise. Clockwise is negative because your general direction for moment anti-clockwise positive. This is clockwise, so negative. Always remember to put in the value, the unit there. In static, we like to play with kilonewton or Newton sometimes. And sometimes we change the meter into cm or mm. But you still at the back, you still need to change into unit SI. So from here, your moment at B equal to 15 kilonewton meter. Okay. So you might ask, hey, Dr. Ang, can I omit the dot or not? Can. You can just write kilonewton meter. This is just for later when you need to do dimension analysis, then it will be very helpful. Okay, so you have done for the left hand side. Okay, then you do right hand side. Okay, so now you do C, yeah. Just now is AB. Just now is AB, yeah. Now is AC. AC means you move a little bit towards right side of the 6 kilonewton. Okay. So what you do is you draw the section C, and then you put in all the external forces that you see in the question and form your free body diagram. So 3 AY normal forces because you cut it, right? So when you cut it, always have normal forces, shear forces, bending moment. Okay. Y is going down because we are using positive shear forces. So on the left component will also go down. And there's a moment anti-clockwise for the left-hand component. And don't forget, yeah. So there's 6K is missing, all right? Okay. So here, again, what is missing here? 6 kilonewton missing. So error in the slides here. You should draw 6 kilonewton at the C point there. Not C point, but just near to the C point. Yeah. So then you solve all the force equals 0, all the moment equals 0. Because this is a 2D, so only solve for Y and X. So this is just a quick answer for you. So if you solve all the force equals 0, again, direction is important. So this notation will help you to avoid careless mistakes. So all the force to the right positive. So here you only have one X direction, so NC 0. Fy, AY go up, positive. 6 kilonewton go down, so negative. VC go down, also negative. So your VC is negative 1 kilonewton. Here is negative. Again, now you start to get negative number already. Meaning what you draw here is wrong. Not wrong, but what you guess is incorrect. You can either redraw or here you can add a note there. VC equal to 1 kilonewton, go up. Because this negative value represent what you draw here. Negative means what you draw here is actually flip up. It's opposite direction from what you draw. Yeah. All right. So moment at C also same. Moment at C, you only have AY multiply 3, and AY is clockwise, but our general direction for moment is anti-clockwise positive. So that's why AY is negative multiply 3. That's why you substitute negative 5 kilonewton there. So it's always safe you write AY first before you substitute value. In this case, because I want it fast, so I just substitute value. So just to be safe, try to write the unknown first. If not, who knows? Because in exam we make mistakes, right? So don't snowball the mistakes, careless mistakes. Okay. From there we find MC equal to 15 kilonewton. Here positive value because the direction is anti-clockwise. So when you compare side by side, A and B, B point, C point, then you know. If you look at different section, the shear force is different. Right? Just now, shear point at B is positive value, right? Okay. So this is just to show you the step on how you solve. All right. Okay, again, just summarize what we learned so far. First, when you see internal forces question, what you do, solve external forces first or solve support first. Don't go into the detail. Look at the diagram, solve for the support, convert all the support into forces. Then convert into free body diagram. Once you have the free body diagram, solve for the resultant first, if you can. Right? Now, normally, you can solve for the external force first. That you learn from chapter 1, 2, 3, 4. Once you have external forces, then only you follow the question. It asks you to cut where, then you go and cut. Then use the positive notation for shear, normal, and bending moment. Bonus moment is this one, MC. Right? Because this is cut, so you need to refer back to this diagram. Always follow this diagram as your guideline. This one. This one, especially the top one, because this will be the cut area. Okay. Can you follow? And we go for another maybe 15 minutes, then we call it a day. Okay. Right. See, our time is until 1 now. Okay. The next example, I just go very fast. So see if you're able to just observe the strategy, the principle that we use. Ignore the numbers, but see how we solve it. Okay. Now, previously, you see all the forces is, we call it concentrated load. Means there's one point of focus area of that force. This is distributed load. Where you find this distributed load, when you have a glue, you glue on something, and then you try to carry the weight. This is distributed load, right? Or there's a bridges, like Penang Bridge. Penang Bridge, there's a rope, and there's that one is distributed load. Okay, I think you have done distributed load. If you don't know, go and refresh back what Dr. Nurul teach you. I just observe how to do internal forces analysis. Okay, this is distributed load. So again, ask you to find the three forces, internal forces, shear, normal, and bending moment at C. First step is to do what? External force or support loading first. So got one support loading here. Support loading is fixed. So you have AY, AX, and also moment A. Direction always anti-clockwise. Okay. Okay. So I show you the free body diagram, convert this diagram into this diagram. Huh? Okay, so this is the distributed load at section C. We use W because it's distributed load. You always see a small signature or small alphabet as a distributed load. Okay, you convert this triangular into this distributed load diagram. So here I just put a highlight that actually there's not necessary to find loading at A in this case, but it's always highly recommended you can find what is A and B. All right. Because distributed load is more easier. There's a way to find the internal loading there. Okay. Yeah. So again, in normal test or final exam, always go and find what is the support load. In this case, if you can find also can. Yeah. So what is important in this diagram? Convert this distributed load of 12 Newton, 12,000, 1,200 Newton per meter into the triangular. Okay. So there's a calculation there. You use the ratio of the triangular. Ratio triangular. So at the length of 3 meter, you get maximum 1,200 Newton. At the length of 1.5 meter here, what is the distributed load here? So you use a ratio 1200 multiply 1.5 divided by 3. You use a ratio. Right, actually half, which is 600 Newton per meter. Which is in this section, at point C is experience 6 Newton per meter distributed load. Sorry, 600 Newton per meter. Okay, so of course you know how to calculate this one in, I think, from chapter 3 or chapter 4. Then what is important is we look at point B and C only. Why not A? My explanation is A, you have a very high number here, 1,200, and also you need to solve for unknown at A. If I only take B and C section, there is no load here. No support. I don't need to find A. It's a smarter way of doing things. Of course, you want to find this section also can. You ask for trouble. Also can. Okay, so let's just accept what happened if you see B and C. You draw free body diagram for section B and C, and then copy the triangular that is distributed load. You know that at section C here, you find is 600 Newton per meter, right? So you write WC there. WC means distributed load. Sub C means at point C. So this notation is important when you do higher level like solid mechanics or in your simulation later. This one, the software will ask you to key in this value, distributed load at what is the things. Okay, so this one I think have been covered in one of the chapter. There's an appendix to find distributed load. So this is one of it. Usually if this question come out, we'll give you at the back of the question. So this is a triangular, so we look at this formula. So this formula is always at the quarter of the triangular. If you have a distributed lot triangle, the center of focus of the weight will always quarter of the shape, quarter of the load. From the base, always quarter. Area is the triangular area, half base multiplied by the height of the triangular. Then this is x prime, y prime means the central of focus. This is from the appendix. If this kind of question come out, we'll sure give you one. We don't expect you to memorize. Okay. So here, why I put 0.5 based on appendix is always quarter. The focus point always 1/3 of the from the base. The length of BC is 1.5. 1.5 divided by 3, you get 0.5. Okay. So this point is from this appendix. Then you put in the force there. This force here is you take the area of the triangular, half 600 multiplied by 1.5. Okay, this in the appendix, this area actually is the weight of the force that acting at this point. At this point, so meaning how to convert this distributed load into a focus load is use appendix area formula. Don't need to memorize one. You see the appendix, you find the A. The A is the focus load. Means you convert triangular into arrow. Arrow is half 600 is this one. Is your H. Your H is 600. 1.5 is the length. Yeah. Then we start to put in the three brothers for internal loading. Three forces, not three forces, three load with is normal force, shear force, and bending moment. So go to that cutting, right? You cut here, right? You cut here, consider left, right? Right. So all opening always pointing up. This side point up because this is considered right hand side. If you refer to the diagram I showed you just now, right? You cut here, so BC is considered right hand side. Right hand side, BC go up. Left hand side, BC go down. Okay. Then moment, right hand side, clockwise. You have to be very clear which component is it. When you cut it, it is left or right. Then you go use the positive notation diagram. You should always understand now why this time AVC go up, why this time MC is clockwise. Because when you cut, section CV is on the right. On the right, So what's the next steps? One, you have the moment diagram already. This one, Yeah, this one, you clear already. So here, here I just have a test If you refer to my notes, MC should be anti-clockwise, right? If you refer to the previous notes I gave you, right hand side, we always have like this, right? But what happened in this example, I purposely flip the direction and see what happened, right? So this is just a highlight, It's just always follow anti-clockwise, but in this case, we try to do error. What happened if we do error? Okay. Again, solving these three equations. X direction, you only have one. NC equal 0. Fy, you have two forces, the green arrow and the red arrow. Before I forget, always when you see focus distributed load, your ultimate goal is to convert the distributed load into focus load. Don't get tricked by the distributed load. Always convert the load into focus load. Then solve it like a normal focus load problem. If you see distributed load and final exam don't give you the appendix, you can raise your hand and ask for the appendix. Because we don't expect you to memorize that one. Okay. Vy, we solve for y component. So Vc equal to negative. So Vc equal to 40. Newton. Typo lah. You calculate, but the concept is there lah. Okay. So here MC anti-clockwise is positive. So in this case, MC is clockwise, so negative. So your MC is negative. So what does it mean? It means the direction in your diagram is you estimate wrongly. The correct one is clockwise. So always follow the positive notation. In this case, we just showcase to you, we flip the direction of what happened if we don't follow. You still get negative value. At the end, you still need to flip it back. Here, okay, how you go this one? Let's say you follow the same answer and then you arrive at MC. You get MC equal negative 225 Newton meter. The next what you write here, MC equal to 225 Newton meter. Here is what? Clockwise, right? Here you convert to positive, it becomes anti-clockwise. Anti-clockwise. You stop at this one also can, but it depends on Dr. Nurul lah. If I set the question, I always ask you to redraw the diagram. Yeah. So always follow this is just to show you what happens if you still want to go your way of converting the direction. You still get negative and you still need to convert back. Always use a positive notation. Okay. The rest is your homework. Go and see. I think our time is almost there. Again, when you see distributed load, your job is to convert into focus load. Okay, what I need to highlight here is C and D. C and D always draw an axis following the center of the body. This line. Some of you, when you break the two body, you will confuse how to connect C and D. Because there's a force here along this axis. You read my slides. This is external force already. You should be covered in chapter 1, 2, 3, 4 already. Yes, I will upload in Engine Max Island. I will share with because I don't have island access for statics. Okay. Okay. Let's see what is our next class. Our next class Wednesday. Okay, static Wednesday, right? Okay, this go home and see. What else? Okay. Wednesday we do diagrams. Okay, see you guys. Dismiss here. Island.